In the next section, we'll look at some classification for different types of randomization, randomized algorithms, different types, how you can use randomization. And that will also influence a bit how easy they are used for certain applications. And let's start with the easiest one, the Las Vegas algorithms. And these are all named after casino gambling towns for no particular reason. I mean, there's randomness involved in gambling for sure, but it's going to be Monte Carlo and Las Vegas algorithms, and why one is one and the other is the other remains unclear. So we'll consider here a general problem to compute, so some function that maps some input to some output strings, but it's a complete function, total function, and unambiguous. If you want to model decision problems, as we will do in the next unit more intensively, then really what you're looking at is a language, and the output is just 0, 1, accept or reject. You could also say that's the characteristic function of the set L. But the setup is general. You can also produce outputs. Then a Las Vegas algorithm is a randomized algorithm A, where we have 3 conditions. First of all, it should always terminate, but only almost surely. So there's a probability 1 for it to stop, but it might potentially run forever, in like the example of the roll die procedure we had last time. The algorithm should always answer correctly, or the only thing we allow it is to output a specific signal. I kind of failed. I don't know what the answer is. But there's a benefit from having this signal as opposed to just an arbitrary wrong answer where the algorithm is confidently saying, yeah, that's the answer, and it's not. Here we're getting this signal that something failed and you can't reliably have any answer. But for each input, the algorithm either produces the correct output, the single unique correct output, or this I gave up. And it should at least half of the time, in terms of probability, produce the correct output. If it always said, I don't know, then it wouldn't be much use. Now, it turns out this definition is generous, and you can restrict parts of it without losing any problems that you can solve. So every Las Vegas algorithm that satisfies these 3 conditions can actually be slightly strengthened. And in particular, you can get rid of this I don't know state. You can transform an algorithm into a new Las Vegas algorithm, which now has probability 1 to output the correct answer. I guess here, unlike in the case of termination, if you terminate with positive probability. So here it's written as probability is 1 to output the right answer. But I guess you can say it never outputs anything different, because whenever it terminates, it does so because of an input that has positive probability. So this really means we can never output anything else. It's not just almost surely. If you care about the difference. We have to pay a little bit for this. So the expected time that our new algorithm takes is bounded in terms of twice the time that the algorithm previously took. But we only get a guarantee for the expected time. But still, that's good enough, and the algorithm, often good enough, I guess. And the algorithm is still a Las Vegas algorithm, so it still terminates almost surely. You'll see how this works in full generality in the exercises. It's a, I think, insightful little construction. Now, you can also go the other way around. Here, in this first part, we essentially got rid of this don't know version. You can also get rid of the possibility that the algorithm may not terminate in after a fixed number of steps. So you can also take any Las Vegas algorithm. Okay, this is the more general version here. Any algorithm that just has probability 1 to output the correct answer, always answers correctly. You can transform it into one. So here we have no guarantee on the time, right? It can be transformed into one that is at least correct half the time, as for Las Vegas on the previous slide. And you have a guarantee on the time, namely the time on any fixed input. So this is a worst case statement because it holds for all x. The time that this algorithm takes is at most twice the expected time of the thing you started with, but it always terminates after that number of steps. So not just with probability 1, but always, always. Okay. You'll also see how to do this. The general construction is not very hard. I'll just want to show you some example in a minute. To introduce some names for this, so both of these variants, an algorithm that is always correct but may not always terminate, or an algorithm that most of the time is correct but may occasionally say, I don't know, but at the expense of that, always terminates after a bounded time. Both are known as Las Vegas algorithms. And so we don't have good terminology to distinguish them that would be established. I try to give them some names so that we can refer to them in the exercises. So the first version is the always decisive algorithm because it never says I don't know. And the second type is the always terminating one for hopefully obvious reasons. All right. In a concrete example, it's often not that hard to make that transformation. Remember we had this roll die procedure, which did a perfectly random sample out of 6 numbers, but it had this infinite loop, potentially infinite loop, even though we convinced ourselves it's only a measure 0 set where it wouldn't terminate and the expected time is actually constant and all that. You can transform that into a Las Vegas algorithm of the other type by just not doing the loop, but outputting don't know if the first attempt failed. And that's not too far from the general construction. Las Vegas algorithms obviously have the benefit that they don't make mistakes, even if the running time is not always predetermined. So especially the always decisive version is useful if you want to use it as a drop-in replacement for some deterministic function. And well-known examples exist where, again, the output is always the same, right? Quicksort never not sorts. It's just that the time it takes is random and can be larger or smaller. But in these cases, you also have the combination of these two properties from the previous slide, right? Quicksort and quickselect, they are both always decisive and always terminating. So again, examples that once you're at this, in not too bad examples of problems, you can get both always terminate and always correct. Okay. Now, the full power of randomization may come only at the expense of accepting wrong outputs. So far, that's unclear. It's just a claim, but to set the stage, let's do the definition for that case too. It might be much easier to allow a randomized algorithm to output something wrong, and we just don't want that to be arbitrary so that it's still useful. And there's 2 slightly different ways how you could formalize this. This is then called a Monte Carlo algorithm, the Monaco version of Las Vegas, or I don't know, the posh version of well, whatever. Again, why one is called Monte Carlo and the other Las Vegas, I don't think there's a good mnemonic. Both is probably going to end expensive. Monte Carlo algorithms are only expected to be correct for half of the time. And then the question is, do they have a bounded error or an unbounded error? Which looks very similar, but really the difference is whether you have a fixed constant away from 1/2 that doesn't depend on the input and cannot shrink with n to 0. Whereas the unbounded error could essentially allow that. So you could say it's the same as above, but you swap the quantifiers. right? For every x, there is an epsilon, so that the probability is stricter than 1/2, but the epsilon may depend on the input. Whereas here, it's crucial that this error probability is independent of the input. And this may seem like a nitpick, but we'll see that's important for theoretical and practical reasons. So in particular, it's maybe worth stating what the definition does not say. In particular, it doesn't say anything about the other cases. If the algorithm has to be correct with little more than half the probability, what does it do in the other cases? We don't care, okay? It might output some arbitrary value, and I guess the definition doesn't say whether it terminates. We'll usually see that you can enforce termination in this case. Basically, if it runs too long, you just output something random. If you can make sure that this doesn't happen with too big a probability, that's fine.